All right, this is Science 8, Unit 3. This likely will be one of the final lessons. It's on pressure, so it's the second half of pressure. And specifically, we'll be talking about Pascal's law, hydraulics, and pneumatics. You may have heard of these before. Possibly not Pascal's law, but you might have heard of Blaise Pascal, which is Pascal is the measurement, the unit for pressure. One thing I wanted to kind of specify and maybe clarify a little better from the previous lesson is that gases compress. Okay, so for example, if you have some sort of, I meant to draw these the other way. Let's redo that. Let's say you have a balloon, it's got some gas particles in it. Let's say it has 6 gas particles. It's able to compress and become quite a bit smaller, okay? Whereas liquids, let's say these are liquid particles that fill this thing up, you're not going to be able to compress it a whole lot, if at all, okay? It's the most you could is that amount, and that would end up causing it to break. Why? Because if we look at particle theory, gases are much more spread out, whereas liquids are quite a bit more filled. So yes, liquids don't compress, at least not easily, okay? That's just one little clarification I need to make from last lesson. And solids, they certainly don't. Now, when I say easily for liquids, I've heard that there are a couple exceptions that are being researched right now, but I'm not sure what came of that research yet. We'll be able to see this in the final little activity that I'll share about the diver bottle. You'll see that liquids don't compress, whereas the gases do. So let's move on to talk about Pascal's law. Pascal's law, this guy named Blaise Pascal observed something, and he came up with this. He says when pressure is applied to a contained liquid, that pressure is transmitted without losing force in all directions throughout that entire liquid. So, for example, let's say this is filled with liquid. It's a container filled with liquid, and there's this metal piece here with a metal bar, and we push down on it. That pressure down gets spread throughout the whole container so that it is all equal every way. A couple experiments that Blaise Pascal did to do with his law was he would have taken a container, put 2 holes in them around the side, and filled it with liquid, and then maybe there's some things plugging that container, and he pulled them out and saw how far the water was projected. And he found that it was the same distance away. It was the same radius, so to speak. Because it is an equal amount of pressure. So the pressure of the fluid going down the can is the same as the pressure that is pushing out. And as the level of the water went down, he saw something happen. I'm going to get you to, if you can, try doing an experiment. You're going to test this question, and this is one that he also did. He said, how does pressure change as depth of water changes? So what you do is you get a carton or a bottle that has a flat side, and you put some holes in the side. Cartons are a little easier, that's why they suggest doing it. Put some holes in the side, maybe push a pencil through. If you're doing something that involves a sharp object to cut it, get some help from a parent. And then you're going to maybe plug those holes while you fill it with liquid. Put this over a deeper baking tray, kind of one that you might make a cake or cinnamon buns in, a bigger one, and stick this at one end, and then remove the plugs and see how far this is. So see how how does the pressure change as the depth of water changes? So if one of these shoots further, that would suggest that there would be more pressure from it. If one shoots not as far, it would suggest that there's less. So you could take a ruler and hold it up to the side and see how far it is. I encourage you to do this activity. And if you do, send me some pictures of you doing it or just a list of your results. Now we're going to talk about something called hydraulic systems. You guys may have been to the fair or in previous years, sadly probably not this year, and you've probably went on rides and you hear those psh, psh sounds, those big hoses, or maybe you've seen a car crash and maybe someone's trapped and they need to open up the vehicles and they peel it off with these things called the jaws of life, registered trademark, in helping to get people free. They use hydraulic systems. A hydraulic system is simply something that uses liquids in a confined space to transfer force. So right here, I've actually made a hydraulic system. I've used these plastic syringes and connected them with a tube. Now, if we look really close at one of the tubes, it's filled with water. Okay, so I'm using water as my hydraulic fluid. And it's closed and it's connected here to this other tube that's filled with water. And there's a piston on each side. It's a rubber sort of thing that's keeping the water from being able to get out. So it's just a little pusher on either side. And I have it lined up so that it's at, let's find my camera. It's at 5, right? So the edge is at 5. These are milliliters, okay? So both of them are lined up with 5. What's kind of interesting is if I push one of them, so let's just kind of do this. It doesn't matter really exactly where the tube is or how it's situated. I can have it curve a lot of different angles. As long as this doesn't pinch off the flow, I'm able to push one side and watch what happens to the other. So as I push down one side, the other one extends. So as I push, that one's extending. So right here, I push this so it's at 0. And what's 5 plus 5? It's 10. And if we look at where this one's lined up with, it's moved to 10. If I push 3 milliliters out of here and move it down to 7, I'd expect that there'd be 3 in my other tube. Right? Yeah, it's at 3. So the amount of force that's pushed down on one of these tubes, it gets dispersed throughout and it will equal the pressure on the other side. So the fact that these have the same surface area, these tubes, it's going to move an equal amount, okay? The pressure it's equal. And Pascal's law says that it is transmitted without losing force in all directions. So it's going to move throughout the entire system. And it's going to have an equal amount of force. Now, if I were to put a weight on top of one of these and then try to push it, that might change how much it goes up, and it wouldn't go up maybe quite as much because there would also be the force being pushed down by something else. So if we think of maybe a car lift, which is some system that does use this, let's look at a picture. For example, here's a hydraulic system that they use to lift cars inside of an auto mechanic shop. It's essentially this same thing, except there's one little difference. We've got a much bigger area here, much smaller, and he's just pressing a button that turns on a little generator that does it. But you know what? They actually used to have some pump jacks, which I'll show you one that I actually have in my car. And it works the same way, that it ends up causing a lot more force. So there's not as much force needed over here as there is over here, and we'll do some math to show how this works. But this is another type of hydraulic system. You've got this connected system here with this equal pressure inside of it in all ways. But notice the amount of pressure that's pushing up on here would probably be 1 or 2 arrows if these arrows were rotated, whereas it's quite a few because there's a lot of surface area here. So there's a lot more pushing up on that. So we'll have a look at this. Let's go back to when it was the same size. When it's the same size, the amount that it moves down, the amount of force that pushes this down is going to be the same amount that it moves up. But it changes when the input and the output are a little different. When we talk about input, that would be the side where this guy is, pushing some force down. This would be the input side, and the output would be this other side over here. All right, so let's look at this. So yeah, let's pretend that this is some car lift kind of thing to lift up a car so someone can go under and do an oil change. And then there's a thing here that's basically going to cause some pressure to go down on the other side. Now, what we know because of Pascal's law, because the pressure in a fluid or a liquid is the same throughout, we know that the pressure over here by this force is going to be the same as the pressure here. So both pressures have to be the same. Now let's use some numbers. Let's say that this area is 0.5 meters squared. So the area of this piston that's pushing down, okay? And let's say that the area over here is 8 meters squared. So it's quite a bit bigger, okay? So half a meter squared and 8 meters squared. Quite a difference. And let's say that vehicle that we need to lift, or maybe the biggest vehicle we'd ever need to lift in our auto mechanic shop, was something that would create a force down that would be 64,000 newtons. That is about 14,000 pounds for those who are wondering. Let's see what sort of force would we need to get over here, okay? Now, if we know that the pressure of the input would equal our force of our input divided by our area of our input, and we know that pressure of our output would be the force of our output divided by the area of our output. Oh, I wrote an I accidentally. If we know that those are our ways of figuring out what the pressure would be, we also know that the pressures are equal. These pressures are equal. If PI is PO, that means that PO is the same as FI over F area of I, the input, or that the pressure of this is equal to these, right? Which means that the force of our input divided by our area of our input would have to equal the force of our output divided by the area of our output, right? If these pressures are equal, then whatever these things are equal to must also be equal to each other, okay? And with this, we already know our area and our force of our output and the area and force of our input. So what we can do is do a little math here, and we can find out that the force of our input divided by 0.5 should be the same as this 64,000 newtons divided by our 8 meters squared, right? And we also know that if we are dividing this side by 0.5, we can multiply both sides by 0.5 and we'll end up with our answer. So 64,000 divided by 8 would be 8,000. Okay? And 8,000, make it a half of that, would be 4,000 newtons. So what is our, this would be 4,000 newtons we just found out. So we need 4,000 newtons to be able to push down whatever method we use. I'm going to show you how a bottle jack works because you could use a similar system to do this, but we need something that can deliver 4,000 newtons down in order to then have 64,000 go up. So if you have a small piston with just a little bit of force, you can actually make it seem like there's a whole lot more force pushing up. So this is a hydraulic advantage. You're able to maybe not use so much. 4,000 newtons, sorry, I pressed stop there. 4,000 newtons is approximately, 900 pounds, okay? So you'd only need 900 pounds down. You could use the same way of coming up with this. As long as you know 3 of these things, you could find out the other one. You could maybe say, how small of a piston would I need in order to be able to just stand on it, knowing that, one human is about 600 newtons. And then you could just stand on this and it would lift a car. So this causes a mechanical advantage. You can set things up physically to make it so that you have an advantage. That you can seem to create more force on the output than you actually are able to on the input. And this is why hydraulic devices are so useful. They use them often in construction vehicles like those diggers and different things like that. Hydraulic systems can also be used as pumps. So I have a pump that I used in my backyard that I ended up pumping a bunch of water out of my yard that resulted from the park behind my house piling all their snow basically right behind my fence. So when it all melted, a lot of it ended up in my backyard, and I had to use a pump that used the same concept mixed with the one that I'll show in a bit with my hydraulic jack that was able to pump some water out of my house without using that much force. Something else that we've studied earlier this year that was also a hydraulic system is your heart. It's a tubing, and what's your hydraulic fluid in it? Well, it's your blood plasma. It is a hydraulic fluid, and this all works by the same idea of the equalized pressure, your blood pressure spreading throughout your body, and it pumps it in some places, and there's valves that keep the blood from going the wrong way, and it works in a very similar way than what I'll show you. So what we've talked about so far are closed hydraulic systems. So those ones are ones that, you know, there's no liquid getting out anywhere, right? It's all staying within the system. But there's also open hydraulic systems. Those are the pumps, okay? So they're able to bring liquid from one place to another. So that's the difference between these two. Bring liquid from one place to another is what the open ones are. They're open, the water can get out, or the fluid, whichever liquid it is. So brings liquid from one place to another. AKA sometimes there are pumps as an example. Okay. Now let's talk about pneumatics. Yes, it starts with a P. The P is silent. It's a lot like a hydraulic system, except instead of water or a liquid, they use air or other gases instead of liquids. So things such as jackhammers or wrenches or drills or those power tools that often get used in auto mechanic shops, they are often using pneumatic systems. And you often hear air being released, like psh, psh. Those sounds. Those are usually going to be the pneumatic systems. Them releasing some of the pressure. So compressors are also an example. So an air compressor is technically a pneumatic system. A biological pneumatic system would be your lungs. They work the same way. Air is moving in and out, and there's pressure is being used to force the oxygen and the carbon dioxide in or out in the way they go. It is a pneumatic system in your body. So let's just look at this chart. It's on page 255 that compares the two systems. There's hydraulic systems and there's pneumatic systems. Like, which one is better? Well, it kind of depends what it's going to be used for. So if we look here, hydraulic systems is on the left, pneumatic is on the right. So liquid filled, gas filled, okay? Liquids do not compress and expand, so they are very quiet and can deliver a force for an extended time. The gases tend to be able to sometimes seep out in some cases. They're loud as they bring in and compress, and they can deliver a short burst of force, but sustained time, it doesn't work so well. So if you're needing to hold something for a long time, hydraulic's going to be better, whereas if it's a quick thing, for example, maybe a jackhammer, a pneumatic system might be a lot better. Here, oils are often used in hydraulic fluids, so oils, they don't freeze, whereas in a pneumatic system, moisture in the air that's being used could freeze. Oils can become highly viscous in cold temperatures, so if it gets cold, sometimes it becomes more viscous, which higher viscosity, it flows a little less, whereas air doesn't in cold temperatures. So in one way, this is better in cold, but in the other, it's worse, and vice versa. Oils need a long time to warm up, whereas air doesn't need time to warm up. It's already ready to go. Oils are flammable, whereas air is not it can fuel, or it can help a fire burn, but it's not the fuel. Oils have a high cost, whereas air, it's free, right? Unless you're a gas station that's charging for air to fill your tire for your bike, which also uses pressure and compressed air. That's another example of a pneumatic system, is those air compressors for your bike. If a hose breaks, a leak may result in a mess, whereas with a pneumatic system, because it's just air, it's not. However, because it's so much pressure, it can whip around and be dangerous. Pneumatic systems are contained systems, so if you're working underwater, it would be better to be a hydraulic system because it's within fluid itself. Okay, it works better underwater, whereas pneumatic systems don't work underwater very well because it needs air to be able to be used. So, for example, scrubbing the outside of maybe an underwater rig to keep it from corroding, maybe that would be best to have a hydraulic system, not a pneumatic system. Here, it also says they do not tend to require as much maintenance for the hydraulic, whereas there's a lot more cleaning and maintenance with a pneumatic system. And they do not give off potentially harmful substances. Usually the oils that are used are pretty natural in the environment, whereas some of the things that get put in to lubricate a pneumatic system can be potentially harmful. Typically, hydraulics can lift more heavy loads for a longer time. Than the pneumatic systems. So having the liquid causes it to be able to do it more, which is why, you know, holding up a car that someone's going to be standing under to work under, it's probably better that it is a hydraulic system, not a pneumatic system. The last thing I want to show you is just a little pump jack, and then there's a video that I'll also put on that I want you to watch that explains how it works. I'm just going to show one outside quick. All right, I'm here outside by my car. Gonna take off my winter tires and put on my summer tires. Probably should have done that a while ago. But here I have a little thing called a bottle jack. It's actually it's a hydraulic system. And there's a little thing on the bottom that you can actually stick this around and rotate and tighten. And what this thing at the bottom does is it changes it from an open system to a closed system. So this is going to tighten it, and at a certain point it's going to be really tight. I've paused so I can fill it up, but once it's tight, I'm able then to take my lever, and I'm just going to tilt it back and forth, and you'll notice the top part of the pump is starting to move up. Trying to hold the camera while doing this makes it difficult. But what it's able to do is push this little piston up, and my force, I'm only pushing down with maybe at most 500 newtons. No, I'm kidding. Probably only 200 newtons of force, and yet right now you're probably going to see my car is lifting up. And I always want to check that I got it in the right spot. There's these little notches. You're supposed to be between the notches. A little bit to one side or the other isn't usually too bad. But you're supposed to be between them. But you just push up, and eventually you get to the top. And this is supporting the weight of the car. Change the tire, put the new tire on. And then, at the end, how do you get it down? You just let air, there's air, and you just let it back out by turning this, and the car drops. Loosen it a bit more. And it should push all the way down. when this was closed, there's no way I would have been able to push that down with my hand. And then just so oil doesn't leak out when I store it, I usually just tighten it, not super far, but just enough that it's sealed. And that's hydraulics, pneumatics for you.